What if the most dangerous volcano in North America isn't Yellowstone, but one you've barely heard of? Far out in the North Pacific, stretching like a broken spine between Alaska and Russia, lies a chain of storm-lashed islands. The Aleutians, remote, wind-scored, seemingly empty. But beneath those dark ridges and smoking peaks, something far larger may be forming. Not just another volcano, not just another eruption, a system capable of altering global climate, grounding aviation across continents, and reshaping coastlines in hours. So why isn't it dominating headlines? What exactly defines a supervolcano? And could one be hiding in plain sight along the Aleutian Arc? The Aleutian Islands sit on one of the most volatile tectonic boundaries on Ophi Earth. More than 40 active volcanoes line this chain. Some erupt regularly. Others remain silent for centuries. But silence in geology is never comfort. It's pressure. It's accumulation. Recent geophysical surveys and magma imaging beneath parts of the Aleutian Arc suggest massive magma reservoirs deep below certain calderas. Not surface lava chambers, deep evolving systems. The kind that don't just erupt, they reorganize landscapes. Most Americans think of volcanic danger in terms of lava flows and ash clouds. But supervolcanic systems operate on a different scale. They don't threaten towns. They threaten systems, climate systems, food systems, air travel systems. Tonight we are not chasing hype. We are examining geology, data, structure, because in the cold waters west of mainland Alaska, Earth may be building pressure, and pressure eventually demands release. Let's step into the science. When Americans think of catastrophic volcanism, one name dominates the conversation: Yellowstone. It's become shorthand for doomsday geology. Documentaries dramatize it, social media amplifies it. But this fixation creates a blind spot. The Aleutian Arc produces far more frequent volcanic activity than Yellowstone ever has in recorded history. And unlike Yellowstone, it sits directly beneath major trans-Pacific flight corridors and near critical military infrastructure. The problem isn't that people underestimate volcanoes. It's that we misunderstand scale. Most eruptions are localized events. Ash falls, flights reroute, communities recover. But supervolcanic systems operate on magnitude thresholds. A volcanic explosivity index of 7 or 8 doesn't just produce ash. It injects sulfur aerosols into the stratosphere. It alters sunlight. It cools global temperatures. The 1991 eruption of Mount Pinatubo lowered global temperatures by about half a degree Celsius for nearly 2 years. That was not a super eruption. Now imagine something 10 times larger. The Aleutian chain sits at the boundary where the Pacific plate dives beneath the North American plate. This process, subduction, continuously feeds magma into the crust. Over time, magma bodies can merge, expand, differentiate. Ignoring these systems because they are remote is a strategic mistake. Air travel across the Pacific carries millions of passengers annually. Cargo routes depend on predictable skies. Military logistics rely on stable infrastructure in Alaska. Volcanic risk here is not hypothetical drama. It's infrastructure vulnerability. The real danger isn't panic. It's complacency. And to understand whether a supervolcano truly exists in the Aleutians, we need to examine the science beneath the surface. A supervolcano is not about height. It is about volume. To qualify as a supereruption, a volcanic system must eject more than 1,000 cubic kilometers of material. That is enough ash to bury entire regions under meters of debris. The Aleutians form because the Pacific plate slides beneath the North American plate. This process is called subduction. As the plate sinks, water trapped inside it lowers the melting point of mantle rock. Magma forms. It rises upward through fractures in the crust. Sometimes it erupts. Often it stalls underground. Over thousands of years, stalled magma can accumulate into large reservoirs. These reservoirs evolve chemically. Gas builds inside them. Pressure increases. If the crust above weakens, the chamber can partially empty in a catastrophic eruption. The ground collapses. A caldera forms. Several large calderas already exist in the Aleutians. They are not cones. They are collapsed scars, evidence of massive past eruptions. Seismic imaging now reveals complex magma storage zones beneath parts of this arc, not one chamber, a network, and networks matter, because interconnected systems can amplify eruptive potential under the right conditions. One powerful example is Okmok volcano in Alaska. In 2008, Okmok erupted explosively after weeks of seismic unrest. Ash plumes rose more than 50,000 feet, disrupting aviation across the region. But the real story wasn't the eruption. It was the warning signs. Scientists observed ground uplift inside the caldera. Seismic swarms intensified. Gas emissions shifted in composition. The Earth signaled its instability. Now imagine similar signals, but sustained for years beneath a larger, deeper system. Today, satellite radar can measure ground movement within centimeters. Seismic networks detect micro earthquakes too small for humans to feel. Super eruptions do not happen without warning. They are preceded by patterns. For viewers analyzing future scientific reports, focus on 3 indicators: sustained uplift, escalating seismicity, and increasing volcanic gas output. Isolated earthquakes are noise. Long-term trends are signal. The Aleutian Arc is heavily monitored by the Alaska Volcano Observatory. This is not blind risk. It is instrumented geology. Still, monitoring reduces uncertainty. It does not eliminate it. And that uncertainty fuels public myths. Myth 1, if a supervolcano exists, it will erupt without warning and end civilization. This idea spreads quickly online. It's dramatic, it's clickable, it's inaccurate. Magma does not appear overnight. It migrates. It fractures rock. It generates earthquakes and releases gases over extended periods. Another misconception is that any large caldera automatically equals imminent catastrophe. Many calderas are ancient scars. Some may never erupt at large scale again. There is also the myth of being overdue. Volcanoes do not operate on schedules. Geological systems do not follow human calendars. In fact, frequent smaller eruptions in the Aleutians may relieve pressure in certain systems, and most dangerous is relative. The Aleutians are sparsely populated. Immediate casualties would likely be limited compared to densely populated volcanic regions worldwide, but ash clouds travel, climate impacts spread. The danger is not cinematic extinction. It is cascading disruption. Science does not support panic. It supports preparation, and preparation begins with realistic scenarios. Imagine seismic tremors increasing beneath a remote Aleutian caldera. Weeks pass. Satellite data shows measurable uplift. Aviation authorities quietly prepare rerouting plans. Then the eruption begins. An ash column punches into the stratosphere. Winds carry fine particles eastward across the Pacific. Flights between North America and Asia halt. Cargo delays ripple through supply chains. Electronics shipments stall. Food prices fluctuate. Within months, sulfur aerosols reflect sunlight. Global temperatures dip slightly. Weather patterns shift. Not extinction, disruption. Military operations in Alaska adjust logistics. Coastal communities manage ashfall contamination. International agencies coordinate atmospheric monitoring. The world responds. Modern monitoring provides warning. Air traffic reroutes. Emergency systems activate. The impact is costly but manageable. The lesson is clear. In a globalized world, even remote geological systems have global consequences. The Aleutians are not isolated from America. They are connected through trade, climate, and infrastructure. Understanding that connection changes how we evaluate risk. So how should informed citizens track these signals? If you want clarity over chaos, start with primary data. Follow updates from the U.S. Geological Survey and the Alaska Volcano Observatory. Watch for sustained patterns, not single events. Ask critical questions. Is ground deformation increasing steadily? Are seismic swarms intensifying over time? Are gas emissions indicating rising magma? Understand scale. Most eruptions fall far below supereruption thresholds. Be cautious with headlines using words like imminent or apocalyptic. Science rarely speaks in absolutes. Context matters. Volcanic arcs like the Aleutians are active by nature. Activity alone does not equal catastrophe. Scientific literacy is a form of resilience. When new research emerges about magma reservoirs beneath Alaska, read beyond the title. Look at methodology, melt fraction, duration, uncertainty ranges. Curiosity paired with discipline prevents misinformation. If you value grounded, science-driven exploration of hidden Earth systems, consider subscribing, not for alarm, for understanding. Because perspective turns fear into informed awareness. And that awareness brings us back to the islands themselves. The Aleutian Islands rise from cold ocean waters like the visible edge of something deeper. Storms sweep across their peaks. Steam drifts quietly from volcanic vents. Beneath them, tectonic plates continue their slow collision, millimeter by millimeter. Magma forms, accumulates, evolves. The geological record confirms massive eruptions in this arc's past. Modern imaging confirms complex magma networks below. Will it produce a super eruption again? No scientist can say when, but the greater insight is this Earth is not unstable, it is dynamic. The same tectonic forces that threaten disruption also build mountains, create fertile soil, and regulate long-term climate balance. Danger and creation share the same engine. For the United States, the Aleutians are not forgotten outposts. They are geological front lines, natural laboratories at the edge of two colliding plates. We cannot eliminate volcanic risk, but we can measure it, model it, prepare for it, and perhaps most importantly, replace sensational fear with scientific clarity, because the most dangerous force is not hidden magma. It is misunderstanding our planet. Out in the North Pacific, pressure builds as it always has, and science listens.